Alright, so I am re-recording the beginning of chapter 11 because the squirrely video from class doesn't have any sound. So this may not quite be the same as what we did in class, but it should still get you covered. Okay. So first thing is, if I just look at, and I'll kind of remind you of what everything we've been over so far this semester, is that we've covered what you do in situations where you have one person, which would be a z-score. You would do a z-test if you had a sample of people, but also understood the population parameters. If you don't have these population parameters, aka you don't have sigma, the population standard deviation, you do a single sample t-test. If you had a sample tested twice, you do a paired samples or dependent t-test. And then this chapter covers what you do when you have two samples. So remember that a paired t-test or dependent t is a repeated measures design, or sometimes called a within groups design. And that means that people are repeated. They take things more than once, or they take two things, but you have the same scores from the same people, or you have scores from the same people. If I decide instead to test two different groups of people because I would like to manipulate my design, so this gets back into experimental design that we covered in chapter 2 or 3, where the only way it's a true experiment is if I manipulate something. I could put people in different groups. Okay. You can manipulate things with dependent t too, but if I wanted people to have separate manipulations, so I can't put both people in the control of the experimental group because that would ruin the study. Okay. So a between subjects design, each person is only in one level or condition, so only one group. Repeated measures, they're in every condition or level or group. So in between groups designs, your sets of participant scores have to be independent. This is an implicit assumption of every test that we've done, but now it's really important that my scores are unrelated to your scores. That's still true in dependent T, but they're kind of dependent because my scores are still my scores in each level, each time point. But in between groups designs, really group 1 and group 2 scores can't be related. In class I talked about an example that sometimes that doesn't always happen. So we have this survey that we like to give participants about their meaning in life. And the survey is like, I feel great, I feel wonderful, everything's wonderful, everything's great. And then they hit this question about halfway through the survey of, I am prepared for death. And they're sort of like, whoa, what just happened? And then the very next question is I feel like suicide is a way out. And both of those stand out, to, at least to me and to participants, as really like sudden moments in this survey. And because they've seen those questions in that order, their scores are no longer independent. Each question is no longer independent. So if you manipulate the order, you get a slightly different answer. And so that would be an example of dependence, where having that set of questions first changes the next answers. So we just want to make sure that participant scores are independent from each other, so there's no relationship between my scores and your scores. Okay. So a quick distributions reminder, and this is where we really got into semantics, small semantics, but if you're doing a Z with one person, it's a distribution of scores, because we're comparing each individual person to other individual people. If we're doing a Z test with samples, where we have a sample, it's a distribution of means, because we're comparing samples to samples. If we're doing a t-test where we don't have the standard deviation, it's a distribution of means still, but we've estimated standard deviation. So that's where standard error comes in. T-distribution of mean differences. So mean differences is paired t, because I'm subtracting my first score from my second score. So each individual person has a mean difference score, whereas deep independent t is differences between means. And that sounds really like just pedantic, but what I'm trying to describe is that we're approaching this idea of null distributions where there's no differences slightly differently. So in dependent t here, what we're saying is each individual person has a mean difference score. So it's a distribution of mean differences for each person. What we're saying here is person 1 and group 1 and person 1 and group 2 are totally different people. So instead we just subtract their means. So it's differences between group means as opposed to differences in a mean difference score of each individual's person's difference. And that distinction between these last two bullets will help with multiple choice questions, but really it leads to the same idea that a null distribution, so what we're testing against is that there are no differences between time 1 and time 2, or in this, for independent t, group 1 and group 2. So then the null distribution, this is just an example, will have 0 in the middle where it's the highest point. It'll still be unimodal and symmetric. So by subtracting my score from my score, I expect there to be no difference. So the mean of that distribution is 0. From subtracting group 1 minus group 2, I expect there to be no difference if the null is true. And so that mean will be 0. So we're approaching this in different ways with the same outcome, that we expect our null distribution to be 0. And that really is handy because it allows us, when we talked about our silly race car example, it allows us to put our race car in the middle and standardize. So T is a standardized score. It's the mean difference in standard error units. And it allows us to determine if if the means or mean differences are greater than we would expect by chance, or greater than or less than 0, where there would be no mean difference. So all that here is in a table format, just so when you're trying to study or trying to figure out for a multiple choice question which one they're talking about. So see, this distribution of mean difference scores is for dependent t. Distribution of differences between means is for independent t. Okay. The other thing that we really covered and we did more of today in class was talking about standard deviation. So in a z-test, standard deviation is given to you. And then standard error is calculated by taking the standard deviation and dividing by the square root of n. Okay. In a single sample t-test, standard deviation is calculated based on the sample, and then standard error is standard deviation divided by the square root of n. Okay. In paired t, it's the standard deviation of the difference scores, so you first have to subtract, and then standard deviation divided by the square root of n, very similar theme here. When we get to independent t, it all goes to hell in a handbasket. And what we have is we have 2 individual standard deviations. So with 2 separate standard deviations, I have to figure out some way to make that one score, because a t-test still only has one denominator. Okay, so we're going to talk about S pooled and S difference here. Okay. So let's talk about that a little more. So this is the formula for variance. We're going to leave everything in variance format because we need it to be squared to work with it in each subsequent step. I did that more today in my second lecture, but this is the formula for variance we've been working with. Okay, it's the same for all single, independent, and dependent. It's just that dependent is on the difference scores. And this is standard error that we've been working with in paired and single t. And it's actually going to be very similar. We're going to use this formula for independent t. Okay. Now for independent t, we're going to add some extra pieces. And while this formula looks really scary, don't be scared. So what's really going on is I'm taking variance here and sticking it in here. This degrees of freedom x is m minus 1 for group 1. This df total is m minus 1 for group 1 plus m minus 1 for group 2. The degrees of freedom isn't really changing. It's just that we have 2 groups, so we add them together to get 1 degree of freedom. And so what this is pooled variance. Remember, I'm trying to go from having 2 groups and 2 standard deviations to 1 standard deviation for the t distribution that we're going to estimate. And we're going to do that by weighting an average, a weighted average. Okay, so this isn't perfectly an average where you just add them up and divide by 2 unless the number of people in each group is equal. If I have 8 people in each group or 10 people in each group, whatever, this is an average. However, if I have more people in one group than another, so let's say I have 20 in one and 200 in another, that's a little extreme, but you would be more inclined to believe the 200 group because you have more data and you're more confident in when we have larger samples. So you would want to weight your statistic towards the larger sample. And so what this formula does is it's a weighted average. It weights it heavier for the larger sample sizes. So you fill in degrees of freedom 1 divided by degrees of freedom 2 total times variance plus same thing. Now, S difference is a complete misnomer. I think this should be called standard error pooled, or just standard error, really. But don't take this as S of the different scores. It's the standard deviation of the t distribution when it's group 1 minus group 2 for independent t. So I feel like S difference is really like a terrible label for this because it makes it sound like it's a dependent test. It's not. It's independent t. So just remember the formulas or the wording here. Okay, so it's still standard error of the mean, and this is standard error of the differences between group means. So that kind of goes back to this table too. But what S difference does is it takes SM. Well, where the hell did SM come from? Because this is S pooled. Let me back up a slide. This is S pooled squared divided by n plus S pool squared divided by m. It is very tempting to do S pooled divided by the square root of n plus S pooled divided by the square root of n. Don't do that. Wait to take the square root till the end. Okay. All right, so the test statistic, so this is step 5, isn't really changing. And I guess one of the big things I really want to stress is that we've done the same thing all year. We've just modified it depending on the type of research design. And so with Z, I had standard deviation, so it's mean minus mean over standard error. Single t is mean minus mean over standard error, which I had to estimate. Mean minus mean over standard error, but impaired t, so this really say mean difference here. But it's still mean minus mean, right, divided by standard error, but we assume that mu m is 0. So it's mean difference over standard error. And independent t is mean minus mean over standard error. So that should sound very familiar. It should sound kind of be bored at this point, right? Everything on the top is always mean minus something. You have population mean, time 1, time 2, group 1, group 2. And the bottom is always standard error. We're just estimating each slightly differently based on sort of the parameters we're given with the research design. And technically, independent t is actually mean minus mu minus mu. But we assume this mu minus mu is 0, just like we assume in dependent t that mu m is 0. So it drops out of the equation because we assume that this subtraction is 0. You don't actually have to. Before this course, that's what we've been doing. Just like we assume here that this is 0. Now in single t, we didn't. And a z-test, we didn't. So you can actually change your mind and do something else. But in general, paired t and independent t, we assume mu is 0. Now with degrees of freedom, it's been n minus 1 all year. N minus 1, n minus 1, n minus 1. So single sample is still n minus 1. Paired samples is n minus 1. So don't forget, with paired samples t, you have one group of people tested twice. So be very careful, because we import them the same in R, that you understand that that's one group of people. It's 8 columns, and each person has 2 scores. Whereas independent t, not 8 columns, 8 rows. If I have 2 columns, they're going to be different groups of people, which means I have 8 for one group and 8 for another group, and that's 16 people. Not 8. Okay. So I think the hardest part here is just remembering what is n. Who's being tested where. So independent t, it's n minus 1 plus n minus 1. Right. So these are the same steps that we've been doing this whole time, blah, blah, blah. So we're going to apply this to a very specific example. So let me load that bad boy. And I put the worked version of this online. But I will pretend to work it a little bit here so that you can see the whole thing worked from this video to the next one. So I had a graduate student make this example up. I thought it was pretty funny, so I stuck with it. So YouTube's giving an award for their Let's Play channels. And they've narrowed it down to PewDiePew and Game Grumps. And they've both been awarded most popular. So we're trying to determine, are they really the most popular? We pulled 8 random videos from each channel and looked at their number of views. So, are they significantly different? So that first step is still all about the assumptions, and we actually added one more here. We talked about homogeneity. So I'm going to sneak that into the notes too, so that you have it later. So the assumption is homogeneity or equal variances. And the solution is to do a different test. Okay. All right. So let's go through and work these. So the assumption here is the DV scale. Yes, because it could be 0. No one could watch any of these videos, so I'd say it's a ratio scale. Did we randomly select? Well, since this is YouTube and I have access to their entire channel, I could randomly select 8 videos. So it says randomly take 8 videos. So yes, I couldn't randomly assign though. If you randomly select, you're actually good, but also think about whether or not you can randomly assign. Right? Is it normal? Don't know. And n is less than 30, so I can't assume that it's normal. Last one we talked about was homogeneity. Oops, which I can't spell. And what you want to do for this one is look at the variances. Or the SDs, either way. And I am not there yet, so I'll have to come back to this one. The next step is to list the sample, population, and hypothesis. So for my sample, I'm going to do group 1 minus group 1 versus group 2. In theory, the population is though that group difference will be 0, so mu minus mu equals 0. But to really distinguish this from dependent t, what we're actually going to do is just type sample 1 over here and sample 2 over here. Okay. So we got Game Grumps and, oops, don't hit tab, PewDiePie. Okay. And that helps distinguish from dependent t, because remember, dependent t is the mean difference of before and after is 0 or it's not. Okay. In this particular example, we're trying to see if they're significantly different. So we're going to use a two-tailed test. So it's not equal and equal. Remember, the research is first. Now for step 3, the finishing step 2. So we can list that as group 1 and group 2 in R, research and Null. That'll help us distinguish between independent and dependent t. Remember that you can do not equal to and equal to, greater than, less than and equal to, or less than and greater than equal to. Those are your 3 choices. Do watch what order you put them in, because that's the order you should use them in R in. Step 3 was about listing the descriptive statistics, and we only got like halfway through this, but I will kind of walk through this now. Because that was a weird Monday. And what I'm going to do is load up my data into R. It's not that data. Yes. Okay, let me clear all this out. Alright, so import dataset from text file. Let's figure out where we hid this. Alright. Chapter 11, data 1. Okay, import. Alright. So what I want to do to get my means is just do a summary of the data. And the first mean is 3125, and the second mean is 6.50. I'm going to do 3125, 3.50. Okay. Now, this is going to set up for something I'm going to do later, and this is in video 2, but I'm going to write out mean 1 equals 3.125, mean 2 equals 6.50, and that allows me later to run some code that will use those abbreviations, and I won't have to fill the numbers in manually by hand. To get my standard deviation, I'm going to do SD of each column separately. Don't do the entire data set. I'm going to say NA.RM equals true because if I have unequal sample sizes, it will assume that some of the columns are missing. I don't right now, but just to kind of get yourself used to it. So the first standard deviation is 1.73. Oops, keep putting this in the wrong place. The second standard deviation is 2.45. So are they equal? And I would say yeah, it's close enough. And I'm basing that on the fact that they're not like 2 or 3 times each other. So 2 times 1.73 would be about 3.4. So, you know, that's close enough. There are ways to actually test this significantly, but that's a different class. Just like we did for mean 1, mean 2, I'm going to do this as SD1 and SD2. If you do that first, you can just type SD1 down here and SD2 down here to see them pop up at the bottom. Next thing we're going to do is come up with length. What length tells me is how many people there are. Now I could look at this, but it's pretty easy to see there's 8 in each group, but this again, ooh, not that, will allow me to use those numbers again here in a minute. So 8 people, 8 people. That makes degrees of freedom 8 minus 1, 7. And 8 minus 1, 7. And then where we ended this particular lecture was talking about S pooled. But let's walk through this. Yeah, so we did all of this and we saved them. And this is the output that I got from R. And where I was ending was with this S pooled formula. So S pooled is, then this is the denominator for Cohen's d. That's in the next lecture. But it is degrees of freedom for group 1, so that's this n minus 1 part here, times variance, degrees of freedom for group 2 times variance, and then I moved the denominator to the end, but it's group 1 minus 1 plus group 2 minus 1, or n1 plus n2 minus 2, if you just do a little bit of algebra. So why have we been saving this whole time, saving N1 and N2 and SD, so I can plop this thing down in here with all the appropriate parentheses and just run it. And I would get S pooled as 2.12. That allows me then to also do, standard, and I changed this in class today. So it's probably a little better to call it S difference, because that's what it is. And so S difference is the square root of standard error pooled, or standard deviation pooled divided by n plus S pooled divided by n. So the nice thing about saving them, right, saving them here, taking that a little bit of extra time, is because then I can use this formula and I don't have to type in the numbers every single time. And then later, when you're trying to do this for the homework or an assignment, you don't have to remember where you got that number from. So you have like a 6 here, but you don't remember why. Well, up here, you're just changing the column that you're doing and then the means. We can also do the formula for the mean using the mean function, but it's just as easy to type the mean from the summary function, so whatever you'd like there. So for this part, be sure you're saving the separate numbers, so when you get down here, you don't have to change anything. Okay. That'll also help. So let's say if you're working on a problem from the book, and they're like, okay, well, the first mean was 4, and the second mean was 10. Oh, goodness. And each group had 12 people, and then the standard deviation for each group was 6 and 8. I could just type them in here like this, and then use this formula again to get the new version of S pooled and S difference for that particular example from like a multiple choice question or something. Okay. So coding formulas like this and then separating them out will just help you not make a math mistake and allow you to do a bunch of different examples by filling in these numbers and not changing any of this down here. So that's the first part of chapter 11. The second part of chapter 11 should be online briefly.